I thank the organizers for inviting me to give this talk. So I'll be speaking about perturbed random matrices, and I'll particularly focus on outlier eigenvalues and the corresponding eigenvectors. Okay, so let's start with describing the first model. So the first model is inhomogeneous Ardha-Shreni random graph on a vertex set 1 to n. So it's a simple graph, no self-loop, multiple edges, and it's an undirected graph. So an edge is placed between I and j, where ij are distinct with a certain probability Pijn. And if you look at the adjacency matrix of the graph, it's a symmetric matrix with 0 on the diagonals, whose ijth entry is simply Bernoulli with this parameter Pi. Now, there are several examples of inhomogeneous Ardha-Shreni random graph already studied in the literature. The one we studied, that's the parameter of inhomogeneity, is described by f, which is a bounded measurable symmetric function. And the probability of having an edge between I and j is epsilon n times fi by n, j by n. Properties of epsilon n will be talked about when the results come. So such random graphs have been studied in the literature for quite some time. So we consider adjacency matrices of such random graphs. Okay. In particular, we'll talk about maximum eigenvalue. So the problem of studying the bulk of eigenvalues is also there, but I mean, it's not related to this talk. But in some of the pictures, the bulk will come up, and we'll talk about eigenvalues that are separated from the bulk. Okay. So the first case where fxy is 1, that is, it's homogeneous Ardha-Shreni. So it's known that if epsilon n is larger than log n to the power something which is greater than 8, okay, anything which is greater than 8, that divided by n, then look at the largest eigenvalue centered by its expectation, then with this particular scaling, it converges to normal with mean 0, variance 2. This was Ardha et al. In 2013. And they also showed that if this particular xi is this exponent over here. So if xi is between 2/3 and 1, then they showed that the second largest eigenvalue after centering and scaling has a Tracy-Wyndham law in the limit. So second largest eigenvalue in this situation is the largest eigenvalue in the bulk, because the mean essentially pushes one eigenvalue outside the bulk. So the second largest eigenvalue is really the largest one in the bulk. So coming to our setup, f is, like I said, a symmetric bounded Riemann integrable function. We consider this kernel if, if is this operator which takes g to this function, it is an integral operator. What we assume is this operator if is non-negative definite and it has a finite rank. In other words, its range has a finite dimension. So whatever assumptions we had in the last slide essentially mean that it has finitely many non-zero eigenvalues, the θ1, θ2, θd, where d is the dimension of the range. And of course, the set of eigenfunctions form an orthonormal set. So in other words, the function f can be written in terms of the eigenvalues and the eigenfunctions. That's the spectral theorem. And if we assume fxy to be positive everywhere, then the θ1 is the Perron-Frobenius eigenvalue, which is larger than the second one. And the corresponding eigenfunction is positive everywhere. R1x is positive everywhere. Our assumption is exactly the same like that in Ardha et al. N epsilon n grows much faster than log n to the power xi for some xi greater than a. So in that slide, n was downstairs over here, but that's exactly the same. And epsilon n has a limit which can be 0 or something positive. Okay. For most of the results, we don't really care whether epsilon infinity is 0 or not. Although towards the end, in some results, we'll assume epsilon infinity to be 0. Okay. So this is what I just mentioned a while back, the bulk. Okay. So this is a special case of fxy has this form. This is a rank 2 perturbation. Fxy is this guy, indicator x less than half, indicator y less than half, plus twice indicator x greater than or equal to half, indicator y greater than or equal to half. Sorry. Okay. And this is the histogram of the eigenvalues. So bulk of the eigenvalues are here, and you can see these two tiny dots which are separated from the bulk by order of magnitude, and 2 is precisely the rank of this transformation. Okay. So before proceeding, let me quickly define. I'll be using this in a few slides, this word with high probability. With high probability simply means that the complement has an exponential decay of this form. Capital O e to the power minus log n to the power eta for some eta greater than 1. And these are, so when I say yn is capital O HP Zn means it's bounded by a constant times Zn with high probability. And similarly, little OHP means the ratio that goes to 0 with high probability. So let's first talk about the first order behavior of the eigenvalues. Okay, just for the simplicity of this statement, we assume that theta 1 to theta d are strictly ordered. And f has this form. The first result is if mu k a n is simply the kth largest eigenvalue of a n in descending order. Okay, mu 1 a n is the largest eigenvalue. So this simply says that mu k a n divided by n epsilon n that goes to theta k with high probability. In particular, it goes there in probability. Okay? So theta k, we should remember, is the kth largest eigenvalue of the integral operator f. We started there. Okay. Now, the first order behavior actually can be proved quite easily. What we do is we subtract the expectation, and that gives us a zero mean matrix whose entries are essentially independent. I mean, up to symmetry. I mean, it's a symmetric matrix whose upper triangular entries are independent. Okay. Therefore, the largest eigenvalue of an is away from that of the mean matrix by the norm of Wn, and I didn't talk about the bulk of the eigenvalues, but Wn scaled by square root of n times epsilon n has a limiting spectral distribution. Okay, so bulk of the eigenvalues of Wn are of the order of n times square root of n times epsilon n. In particular, the largest eigenvalues are of the same order. Okay, so therefore, the spectral norm is of this order, which is much smaller than n epsilon n. Okay, and therefore, when you divide by n epsilon n, you immediately get that the largest eigenvalue divided by this, it goes to theta 1, and the same for any one of the kth largest eigenvalues. Okay. Now, the question of interest for us is what happens to the fluctuation of the largest eigenvalues. Okay. Now, if this is a simple example, fxy is twice square root of xy. Now, we looked at several replications of the largest eigenvalue, and after centering, it shows a Gaussian fluctuation. Now, why we should expect a Gaussian fluctuation? So answer is easy to explain when it's a rank 1 perturbation. So rank 1 perturbation means, let's suppose fxy is of this form, r1x, r1. So then, like I just said, you can add and subtract the mean matrix and call that Wn. So it's Wn plus the mean matrix, which is n epsilon E1, E1 prime. Okay. And we shouldn't forget that Wn is therefore essentially a Wigner matrix. By Wigner matrix, I mean a matrix whose upper triangle, which is a symmetric matrix with upper triangular entries independent, zero mean. Okay. Now, again, I didn't talk about those results, but Wn scaled by square root of n times epsilon n has a limiting spectral distribution. Okay. The form of the limiting spectral distribution is unimportant, but this has already been talked about in one of the talks. So this is free multiplicative convolution. So free probability was introduced in Raghavendra's talk yesterday. So this is free multiplicative product of semicircular law with something else. That something else is just the law of R1 times U, where U is independent. But for our purpose, it's good enough to know that this is simply a compactly supported probability measure, no more, no less. So what it means that the eigenvalues of Wn are sitting on a compactly supported problem, including the largest and the smallest one. Okay. So this is essentially a rank 1 perturbation of a Wigner matrix, okay, where the subscript n of theta n is suppressed for the sake of notational simplicity. Okay. Now, how does one get the fluctuation in such a situation? So an is Wn plus theta n E1, E1 prime. That was the last equation in the last slide. Let V be the eigenvector corresponding to the largest eigenvalue. That is, if you post multiply both sides by V, then this is what you get. Now V times E1 prime, V when it comes over here, E1 prime V is a scalar, and hence it can be moved to the left. And by definition, V is the eigenvector corresponding to mu max. So An times V is mu max V. Now, if we take this to the left-hand side, then this essentially means mu max times identity minus Wn into V is this theta n E1 prime V E1. And this matrix mu max identity time minus Wn, that's invertible with very high probability, simply because the norm of Wn is much smaller than the order of mu max, which is why this is invertible. And therefore, you can take it to the right-hand side. So V becomes this guy. Okay. So the two steps hidden over here, I bring this to the left side and then multiply by the inverse. Then what we do is we multiply both sides by E1 prime. Okay, so E1 prime V, and then there's an E1 prime coming over here. Once again, E1 prime V is non-zero with very high probability, simply because just like the largest eigenvalue is determined by the largest eigenvalue of F, the largest eigenvector V is aligned with E1 up to a sign with a very high probability. In particular, it's non-zero with very high probability, and hence we can cancel it from both sides. So what we get is 1 equals to theta n E1 prime mu max times identity minus Wn inverse E1. Okay. So let's continue from this one in the next slide. Now, if I again multiply both sides by mu max, the largest eigenvalue, then this mu max will come inside with in the denominator, and this is what we'll get. Now, the reason I gave a minute back for this matrix to be invertible, that is, the spectral norm of Wn is much smaller than the order of mu max, tells us that this inverse can be expanded. Okay, so the inverse can be expanded whenever this is something of norm smaller than 1. And that happens with a very high probability. So if you expand the inverse, this is what you get. Mu max equals to this guy. I mean, there's an abuse of notation. I mean, theta n is now abbreviation for n times epsilon n. Theta n's are not the eigenvalues I started with, but nonetheless, we understand what's going on. Okay, so mu max is this guy. Now, if you look at the first two terms, the first term, this is a deterministic term, n epsilon e1 prime e1. Okay, this is completely deterministic. The second term, now n epsilon n by mu max, this is approximately 1. Okay, this goes to 1 in probability. This is something we talked about in the first theorem. And e1 prime wn e1, wn is a matrix whose entries are independent, I mean up to symmetry. So e1 prime wn e1, Lindeberg central limit theorem will tell us that has a Gaussian fluctuation, again up to a scaling. Okay, entries of wn are zero mean. Okay, I'm just adding up zero mean entries. And then there are a bunch of other terms k from 2 to infinity. This is what I said. If you do the bookkeeping, then Lindeberg central limit theorem will give us this limit. Now, the challenge over here is to deal with the tail, how to take care of this guy. And this is, if you take a closer look at this, this is random actually. But what happens is the expectation, it has an expectation and a standard deviation. The standard deviation is much smaller than the standard deviation of this, and hence the expectation matters. So the way of dealing with the tail is replace them by the expectation, okay? And because the standard deviation is already taken, we have something of a higher standard deviation in the Lindeberg central limit theorem. In one sentence, that's the way to deal with it. Okay. The other question is, the master equation seems to be true only for the largest eigenvalue, but we are talking of a situation where we have a perturbation of a higher rank, okay? How to deal with the other eigenvalues and also the largest eigenvalue in this situation. In this situation, will not have this simple equation, okay? There will be a bunch of equations. Okay, so before I tell you how to prove it in that case, let me first tell you the result. So Ek is essentially the normalized eigenvector of the deterministic thing, the integral operator. So then, if you look at the kth largest eigenvalue, center it by its expectation, then it is of this form, n epsilon n theta k by mu ka. Now, this n epsilon n theta k by mu ka, this goes to 1. And here we have Ek prime wn Ek, which again has a Gaussian fluctuation by Lindeberg central limit theorem. And whatever remains has a fluctuation smaller than this. So Wn is the centered matrix. So as a consequence, what we get is the top D eigenvalues centered by their expectation, they have a jointly Gaussian limit, okay? So if you look at mu k minus expectation mu k and centered by and scale by square root of epsilon n, then it has a multivariate normal limit, and there is a description of the covariance as well. Okay, so this is a zero mean normal random vector with this covariance structure. And once again, the covariance and everything else you can simply read off from, because we have an exact expression, okay, Ek prime Wn Ek. So you just have to calculate the covariance correctly. Now, a special case, if fxy is strictly positive, then the description of sigma square is slightly easier, and that's strictly positive because all these terms are strictly positive everywhere. Now, the rank 1 case where fxy has this theta rx ry, then the same thing, mu max centered by expectation and scaled by square root of epsilon, that has this normal with mean 0 and this as variance. Now the question is, how explicit is the centering? That is, we centered by the expectation. Is there a way to understand the expectation better? So for that, we had to assume a bit more. We had to assume F to be Lipschitz. And let BJL be this matrix where this first term is something that we have already saw, n epsilon epsilon j prime epsilon n. Okay. And the second term essentially comes from the second, if you look at the expansion, the second term in the expansion. The result is expectation of UKAN is essentially of the order of the kth eigenvalue of B. Okay, and B is a deterministic matrix. Okay. So this gives a description of the centering as well. In particular, when fxy has this special form of rank 1, then we can write down exactly the first term and the second term. Okay, and n theta epsilon, there's a theta n over here which has been suppressed, and this is much more smaller. So in other words, there is a description, although not very neat, of the centering parameter as well. Now let us come to the behavior of the eigenvectors. Okay, once again, Ek is the deterministic eigenvector, that is the eigenvector corresponding to the kth largest eigenvalue of fxy. Okay. Now, if you look at Vmax, Vmax is the largest eigenvector of An. Okay, the eigenvector corresponds to the largest eigenvalue of An. Then Vmax will asymptotically be aligned with E1. Since E1 is orthonormal to E2, E3, Ek, Vmax, the inner product of Vmax and Ek for any k running from 2 to D will go to 0. So right now, we know that this goes at this, this is much smaller than 1 over n epsilon n. In a slightly different model, we'll have an exact description a few minutes later. Okay. Furthermore, if epsilon n goes to 1 fast enough, then what we could show is Ek prime Vmax minus this. So of course, I mean, Ek prime Vmax, these are all normalized eigenvalues, eigenvectors, so they go to 0. So in order to have a fluctuation, you have to scale them up. Okay, so what we do is we multiply them by n times square epsilon n. So they have a limit, normal 0 sigma square. Again, sigma square has this description. So what is missing over here is E1 prime Vmax. Unlike these things, E1 prime Vmax goes to 1. Okay, because Vmax is asymptotically aligned with E1. And the question there is at what rate? That is the answer is in a few slides later. Okay. So let me quickly sketch the proof for you. What were the additional challenges that we faced in this D rank, higher rank perturbation? So we defined a D cross D matrix this way. Okay, n epsilon square root of theta j theta L, Ej prime I minus 1 by mu k W inverse EL. I mean, this is something where this should look very familiar when we dealt with the rank 1 case. Now, V is essentially a diagonal matrix up to order n epsilon. Okay, if you divide V by n epsilon, it goes to diagonal theta 1, theta 2, theta D. All other off diagonal entries are of a much smaller order. The lemma that actually came to our rescue is, if you look at the eigenvalues of V, then with a very high probability, they are same as the corresponding eigenvalues of AN. Okay, so this is in a way the equivalent of the master theorem we had in rank 1. Okay, there we had just one equation and that gave us the eigenvalue. Now we have k many equations and they all of them together tell us that the kth eigenvalue of An is exactly the same as the kth eigenvalue of V with a very high probability. And if you look at the entries of V, we can apply exactly the same method as before. We can expand this inverse and talk about the first term, second term separately and proceed. Okay? So this lemma actually helped us do a similar kind of computation for higher rank perturbations. Now, let me quickly tell you how we proceeded in the proof of this lemma. So what we showed essentially is that the eigenvalues of mu k are also the eigenvalues of V, and then we used the Gershgorn circle theorem, which says that if you take a circle in the complex plane of this radius around the diagonal entry, then each of these circles must have at least one eigenvalue. Now, I told you a while back that V is essentially a k cross k diagonal matrix. Okay? So the diagonal entries are dominant. They are of a much higher order than the off-diagonal entries. And hence, since I assumed the eigenvalues to be separated, after a while, the radius shrinks down sufficiently large so that all of these are disjoint. Okay? The Gershgorn circles are disjoint. And hence, each circle contains exactly one eigenvalue. So therefore, from that, we can easily infer that the kth largest eigenvalue of An is exactly same as the kth largest eigenvalue of V. And once that's done, like I told you, we simply expanded the inverse like before. And then we had to truncate, and that's a usual argument. There's nothing new in this situation. Okay, and had to deal with the tail and show that it has a fluctuation of a smaller order. And once again, the first two terms matter and the rest don't. I mean, once you replace them by the expectation. So, I mean, this is standard. What new we had to do is, I mean, this idea of separating the eigenvalues using the Gershgorn circle theorem. Now, this is a really serious mathematical challenge that let's go to the picture once more. I mean, here, what I said is the eigenvalues or the diagonal entries are separated, and hence this radius eventually shrinks to a point so that they become disjoint. But this idea completely fails if these two were the same. They would never ever become disjoint. Okay, so although initially this sounded like a mathematical challenge that would have been easy to overcome, honestly, we do not know how to overcome it yet. Okay, so this entire method completely fails if you have two successive eigenvalues of the integral operator that we started with, which is same. So this works only when you have an isolation of the eigenvalues. I mean, it works fine when theta I is separated from theta I minus 1 and theta I plus 1. It works fine for theta I. And the reason is what I said, the center of the two Gaussian disks coincide, and hence you don't have. And as of now, we don't know any way of distinguishing between the two successive eigenvalues. Yeah, please. Homogeneous case, there's only rank 1. Rank 1. So rank 1, I mean, this problem arises only when you have a higher rank, right? Only when you have a higher rank. Yeah. The moment the perturbation is of a higher rank, I do not know of any way of computing. This method does not. Maybe something else works with this. But let me tell you, give you a very so suppose the simplest possible case. Okay. So suppose you have a bipartite. So this is a homogeneous random graph. This is another homogeneous random graph. Okay. So and they are of the same order. Then what can you say about the largest eigenvalue? So largest eigenvalue, essentially the largest eigenvalue of this and this. Okay, so that's like maximum of 2 Gaussians. Okay, so largest eigenvalue is maximum of 2 Gaussians, second largest value is minimum of 2 Gaussians. So one thing is clear, that you won't have Gaussian limit. Okay. Now let me talk about a slightly different model, a model with a variance profile. So this is joint work with Bishak Bhattacharya and Rajat Hazra. So suppose we have independent zero mean random variables, and by variance profile, so the role played by the inhomogeneity kernel is now the role the same as the variance profile. Okay, we have a function from 0, 1 cross 0, 1 to 0 infinity, which is again have the same properties, bounded, symmetric, and Riemann integrable. And what we assume is the variance of the ijth entry is fi by n, j by n. Let's set up the model. So the Wn is the matrix whose ijth entry is I minimum j, I maximum j. So in other words, it's again a Wigner type metric, that is its upper triangular entries are independent zero mean. And then we perturb it in this way. N is Wn plus theta n, I running from 1 to k, alpha I, ei prime. I'll tell you what are alpha i's and ei's in a second. But before that, let us pin down the assumption. So this is a moment assumption, that is the kth moment is uniformly bounded by k times b to the power k for some b positive. And the assumption on theta n is much larger than square root of n times log n to the power psi, and much smaller than n. Well, okay, it's not much. I mean, this means theta n is capital of n, and this means this guy is capital of theta n, but psi is some constant larger than 4 times beta plus 1 and 8. And as before, alpha 1 to alpha k are strictly ordered positive numbers. And ei prime, I'll tell you in a second what hi is. Ei prime is essentially you look at hi's and normalize them to get an one, where h1, h2 are orthonormal functions in L201. And in addition, they are bounded Riemann integrable. So as before, mu I is the ith eigenvalue of an. Then the first order condition is exactly the same. That is, mu I is of the order of theta n. Mu I divided by theta n is that goes to alpha I with high probability. And the second result is also similar. Mu I centered by its expectation is of this order. Okay, now things have changed a bit. So ei prime WEI, that has a Gaussian fluctuation without any further scaling, and hence the rest being OP1 suffices. Okay? So in other words, if mu I is centered by its expectation, then it exhibits a Gaussian fluctuation without any further scaling. And just like we had in the previous case, we can talk about the joint asymptotics of the top k eigenvalues. Okay, so they are multivariate normal random vector with this covariance structure, which is very similar to what we had 2 slides back. Okay. Now, what is new in this model is we could study the rate of alignment of Vi with Ei. Okay, that was missing in the previous results. So let Vi be the normalized eigenvector of mu I. Okay, so mu I is the ith largest eigenvalue of An, so Vi is the corresponding eigenvector. And just to get the sign right, we assume Ei prime Vi is greater than or equal to 0, because you can have that with a negative sign as well, just to get the sign correctly, nothing else. Okay, so the result is Ei prime Vi minus this expectation that with this particular scaling has a normal with 0 mean limit. And we'll soon see in the next slide what happens when these two I's are distinct. But before that, let me tell you, in this particular case, expectation of Ei prime Vi, that goes to 1 for obvious reasons. That is, Vi is asymptotically aligned with Ei almost surely, hence Ei prime Vi goes to 1, and hence its expectation also goes to 1. It's a bounded random value. Now, when I is not equal to j, then this guy goes to 0, that's the expectation goes to 0, and there you have a different scaling, that is theta n. Theta n times Ei prime dj minus this has this normal 0 sigma square limit. I didn't want to put the expressions of sigma I square on the slide because some expression, okay, which can be calculated, but it's lengthy. Okay, so just a quick comparison between the two cases, I equal to j and I not equal to j. So in one, when I equal to j, the order is root n by theta n square, and when I not equal to j, the rate is 1 over theta n. And it so happens that this is much smaller than this. Okay, so that's kind of expected because in the master equation, when we try to look at Ei prime Vj, essentially Ei prime Vj for all j equals to 2 to k, the variances, they essentially accounted for the variance completely. Okay, so if you look at the variance of Ei prime V1, which actually goes to 1, that's bound to be of a smaller order. Okay, that's the broad intuition. I mean, I don't have any reason, but I don't have any other reason for this phenomenon to happen, but this is what we see. We also showed that if you look at the largest entry of Vi minus Ei, that is much smaller than 1 over root n. Okay, so this is called delocalization of eigenvectors in the random matrix. Okay, so so that's what I want to present. I want to tell you the future directions that we want to go. So infinite rank perturbation, that's another mathematical challenge we are yet to overcome, because all the results that I talked about, they essentially proceed in the direction of writing the eigenvalues of An as those of V, which is a finite dimensional matrix, K cross K. So now when you have an infinite thing, this idea will break down. Then you'll have to write them as eigenvalues of some operator in some, and study that. So that's a mathematical challenge which has to be overcome. And like I mentioned, the case where when you don't have isolation between the eigenvalues, that's turned out to be much more challenging than what we initially thought. Okay, so these are the two serious mathematical challenges that we'd like to overcome.
Thank you, Arijit. Let's thank Arijit for the talk. Other questions? Yes, please.
Ashley, so your future directions were exactly the questions I wanted to ask you about. So what I was actually thinking about is like, can we do some kind of like, quote unquote, varying perturbation, right? So as the matrix size increases, we increase the size of the perturbation, but we make it grow very, very slowly. Like something like, let's say log n or something like that.
Thing like that, or you have a infinite dimension perturbation where
Right.
alpha I satisfies some summability condition, like L2. I'm not sure what was the right condition on alpha I, but some summability condition on those alpha I's there.
Right, and another thing I was wondering about, like the theta I equals theta I plus one thing. So I'm wondering, like, as you increase the size of the perturbation, does it like eventually become like inevitable that you're going to get like some kind of successive equal eigenvalues, or like is it possible to like avoid that case?
So that's kind of the assumption, right?
Right.
So
right,
theta
right.
1, theta 2, that's we're choosing.
Right.
So whether to have them ordered strictly or not, that's a choice that we're making.
That's a true. Yeah, but I'm just basically wondering, like, is that like what like those typical perturbations like will have that, or will they not have that?
No, there are applications where that ordering is not true. For example, the the example I mentioned.
So I guess like we can be sure that such models always exist, no matter how much. Sure.
Thank you. More questions? Maybe I can ask a quick question. So you say that it's challenging when the eigenvalues coincide.
Yeah.
But like, what do you think it's just technical challenge, or is it different behavior?
No, so of course, I mean, we don't expect Gaussian anymore. Then we'll have order statistics of Gaussian, and but technical right now it's more of a technical challenge. Right? Yeah.
All right. More questions? Well, if there are no more questions, let's thank Arijit again for his brilliant talk.